So let's start with some reminders. Not an exam, just reminders. So we're in the business of exactly solving some conformal field theories. So it started by guessing the spectrums based on considerations from the existence of degenerate fields, fusion rules, having integral spins for single-valued nest of correlation functions. And now we want to compute the structure constants, the 3-point structure constants, which are supposed to help us solve the full theory, because by using operator product expansions, you can reduce n-point functions basically to 3-point functions. So to get 3-point structure constants, we are still using the existence of a degenerate field, like this V2 one, which has a vanishing null vector at level 2. And the level of correlation function, it leads to a differential equation. So if you have a 4-point function with such a degenerate field V2(1), this obeys a second order the equation. And we can solve this equation in terms of hypergeometric functions. And then this gives us the conformal blocks in any channel, STU channel. And then we have to combine these conformal blocks in single-valued 4-point functions. So, for example, in the S channel, thematically, the blocks, so it looks like this. So if you have the field 2,1 here fusing with the field number 1, so that's the S channel. And by the fusion rules, we have only 2 fields that can appear in this channel, and there was a notation that these fields were called 1 plus or minus. And then this gave us, by crossing symmetry, this gave us constraints on the structure constants, which appear in front of these blocks. So if you want, thematically again, this 4-point function is a sum in the S channel over some D plus minus, which is a 4-point structure constant, and then this block here. And by crossing symmetry, we could determine the ratio, in particular ds plus over ds minus. And if you look at the structure constants which appear in this ratio, those 3-point structure constants now, I mean, these are C1 plus, and then a big C1 plus 2, 3 over C1 minus, big C1 minus 2, 3. And then we could guess this degenerate OP structure constants and obtain an equation which tells us what this ratio of 3-point structure constants is. So more specifically, we had C1 minus 2, 3 over C1 plus 2, 3. Well, this was a bunch of gamma functions. I mean, here the gamma functions come from the fusing matrix for the hypergeometric function. I mean, yes?
Sorry, Sylvain, can you remind us what is the difference in the definition between the small c, and capital C?
Right. So small c is the structure constant which appears to be this OPE of a degenerate field with some field here. So V21 Vi, let's say, is the sum small ci and Vi plus minus. Big C is basically the 3-point function. And small d is the combination of these two, which appears in this particular 4-point function in this channel. Okay, so using crossing symmetry, we obtain this ratio. And well, let me rewrite it just to as a reminder, and because we will still need it. So this ratio was, well, there are some prefactors, -1 to the 2s2, beta to the 4 beta, P1 plus P1 bar, and then the bunch of gamma functions, 8 of them, in fact, 4 in the numerator, gamma of 1/2 minus beta P1 bar plus minus beta bar plus minus beta P3 bar over gamma of 1/2 plus beta P1 plus minus beta P2 plus minus beta P3. Then we had to solve this equation and get the 3-point function. Well, this equation alone is not enough because it tells us basically, so let's focus on the diagonal CFT, like Liouville theory. So this equation basically tells us a ratio of the type CP1 plus beta over 2 or minus over CP1 plus beta over 2. So it gives us the 3-point function up to a periodic function in P1. But in Liouville theory, we have two degenerate fields, V21 and V12. And the similar equation for V12 would give us CP1 minus 1 over 2 beta over CP1 plus 1 over 2 beta. And now the solution is unique. If beta is unique, provided beta squared is real but not rational, and the function is continuous. And to write this solution, we have to introduce the double gamma function, which is defined by gamma beta x plus beta over gamma beta x equals square root of pi beta x minus 1/2 over gamma of beta x. And the same for beta minus 1. So in fact, you have gamma beta equals gamma beta minus 1. Okay, so this function is what we need because when you shift it by beta or beta minus 1 or beta inverse, you get factors of gamma, which are very much like the factors of gamma we have here. So we define the solution of the equation, of the shift equations, CP1, CP3 equals product gamma beta minus 1 of beta plus beta minus 1 over 2 plus minus P1 plus minus P2 plus minus P3. And this gives us the solution not only for Liouville theory with C less than 1, but also of generalized minimal models and A series minimal models. So all these CFTs which are diagonal with two degenerate fields. Okay, so that was the reminder. So now what's left? Well, we still have a CFT which is diagonal with two degenerate fields and which we didn't solve yet, and which is Liouville with another central charge, basically any complex number which is not less than 1. So do you know why this wouldn't work in that case? I mean, after all, we could guess that maybe this formula is still valid for any complex central charge. And since, I mean, this gamma beta function is basically analytic, so at least we can analytically continue at least in some neighborhood of this line, C less than 1. So we could take this as an ansatz. But that's not true. So do you see why? Or at least why it cannot be true on the whole for the whole complex plane of central charges. Well, okay, it's not immediate based on, it's not a tricky question.
When C is real less than 1, does the same thing as beta being real?
Yeah, so C less than 1 means beta squared is real.
We'll change this way.
Beta squared real, beta is real, as you said.
There are two betas, so maybe that's plus or minus I beta.
Yes, the answer has to do with I beta, in fact. With the fact that now, if you take beta to be pure imaginary, this gamma function, this double gamma function, no longer exists. It has an essential singularity. Let me give an argument why this is the case. So, if you look at this gamma beta of X. Well, based on its definition, you see that it will have some poles. I mean, this gamma function itself has poles, so gamma of X has poles for X negative integer. Gamma beta, if you look at it carefully, it has simple poles for X in minus beta n minus beta minus 1 n. So you see why it's called the double gamma, if you want. This is one series of poles with one integer parameter, but now we have a poles with two integer parameters. And where are these poles? So, for example, if beta is real, well, you have beta and beta minus 1 here, which are aligned on the real line. And so the poles are on this half line, basically. Well, I have a minus sign. I'm ignoring the minus sign now. Okay, the poles are on some half line, but the poles are all isolated in general. So in the vicinity of a pole, you don't find any other pole. Now, if beta becomes complex, well, you have beta and beta minus 1, oops, and the poles belong to some lattice here. That's still very fine. They are still isolated. But if beta becomes imaginary, you have beta and beta minus 1 collinear, but in opposite directions. And yeah, the set of poles becomes dense if beta squared is irrational. So you have near a pole, you can find infinitely many other poles. And this is a sign that your function, in fact, is no longer exists. I mean, one way to see that is to write this function gamma beta of x as a product of a poles, like product in n integer of something like 1 over x minus beta m minus beta minus 1 n. Well, okay, you need some function f mn of beta here for the product to converge. But anyway, I mean, this can converge only if beta is not imaginary. But if beta is imaginary, this thing it diverges. Okay, so this 3-point function we have here it cannot be valid for beta imaginary, but beta imaginary corresponds to central charge greater than 25, which is a regime we are very much interested in if you want to apply Liouville theory to quantum gravity, for example. So we have to do something. And then, in fact, this formula also is not valid. It's only valid if c less than 1, because if you remember, if you looked at the 4-point function of Liouville theory, we did not expect that to be analytic beyond this, I mean, near this this half line because of poles crossing the integration contour. So basically, this, even though this formula is itself well defined, unless beta is imaginary, it's not the 3-point function of Liouville theory, except for c less than 1.
If we are in regime of c less than 1, then what is the proper integration contour for Liouville? Is just the real line, or do we have to do some shift?
Yeah, that was the region where we have to do a shift. So if you are in the p-plane, complex p-plane, and you want to c less than 1 now, if you write an OPE of Liouville theory, VP1, VP2 equals integral p VP, something like that. Yeah, typically due to the contribution of descendants, you have plenty of poles there, so we have to take this this integration line.
So these are poles which are not manifest in the C, because the C itself doesn't have any poles.
Right, C itself is fine. These poles came from descendants, so they came from this F here, which the structure constant which came from contributions of descendants. So if we had an LVP, so descendant with a creation operator L, we have this coefficient which have this pole.
Suppose that we not even convey away, even a little bit away from this C less than 3 less than 8.
Right. So the 4-point function is immediately non-analytic if you try to make C complex. Although the 3-point function is analytic much further.
Yeah. I guess so it's not said that it wouldn't be correct to say that there's an issue with using with this formula for the 3-point function away from C less than 1. It's more subtle reason that we have.
Yeah, exactly. You have to look at 4-point functions. Otherwise, you don't see the problem. Okay, so what do we do? Well, we still have the same equations, which I started erasing, but maybe I should not. So the same equation here. We still have to solve it, but for different values of the central charge. And the trick here is to introduce another special function which obeys almost the same shift equations. And this other special function is it's just written in terms of the gamma beta again, but it's a gamma hat beta of x equals 1. So a special function which obeys almost I beta minus I x. So if you look at this function and look now how it behaves on the shifts, so you get gamma hat beta of x plus beta over gamma hat beta of x equals, here you get an I beta instead of the beta we had there, but otherwise it's the same. And if you look at the shift by beta inverse, well, it's slightly more violent now. So you get also the I beta, but also you get a gamma of 1 minus beta minus 1 x. So you're replacing the 1 over gamma of beta minus 1 x by a factor gamma in the numerator now, but with a different argument.
And what is the determination of the power? If beta is not real. I'm sorry.
Right. So the power now, well, precisely now you want essentially I beta to be real.
Okay.
So that's why we have this this function. So we can now this function gamma hat. So gamma beta, if you remember, was defined for beta squared. Well, if any complex number which is not real negative, and gamma hat beta for any complex number which is not real positive. And so in particular, this includes the half-line C more than 25, so beta squared real negative. So using this gamma hat, now we want to solve this equation, and in fact, the solution is almost the same. Well, almost. So the solution is a C hat, C1, C2, C3 equals. So again, it's a product. Yes, and then we have gamma hat beta. So maybe I want to rewrite this just in terms of gamma itself. So okay, so let me write it in terms of gamma b now. So b is I beta. And then let me introduce q, which was b plus b inverse. So q over 2 plus minus I1 plus minus I2 plus minus I3. So you see, due to this I'm using gamma hat, but gamma hat is inverse of gamma. So therefore, my double gamma function now is in the numerator instead of being in the denominator as it was before. But otherwise, it's a very similar formula, except that I have plenty of I factors here and also there. And that is, in fact, the solution of Liouville theory with any single charge, which is not less than 1.
There is no hat on the gamma function. It's because that's.
Yes, so I have, if you want, I have written it in terms of the original gamma because gamma hat is defined like that.
What's the integration contour now, or P?
So now the integration contour is just P real in the OP because you don't have any poles there, no, not any problem.
And you can convince yourself that there is an overlap region.
Right, so there is an overlap region between these two solutions here, C and C hat, of the same equations, which means that if you take the ratio of these two solutions, what you find is a so-called elliptic function. So a function which is periodic both in beta and in beta minus 1. But this overlap region doesn't extend to the full CFT. So for Liouville theory, there is no overlap region. So you have this region and the other region is C less than 1. That's it. Okay, so that's maybe not how you saw this 3-point function, because it's well known under the name of the DOZZ formula for Dornoto, Zamolchikov, Zamolchikov. And this is not quite the DOZZ formula. So what's the difference? Well, the difference is just a field normalization. So if you remember, I mean, we could renormalize fields by Vp of Z go to lambda P Vp of Z with some scalar prefactor. These scalar prefactors are arbitrary. In the bootstrap approach, you don't have anything to fix this prefactor. But the DOZZ formula comes from not the bootstrap approach, but some Lagrangian approach to Liouville theory. Let me very quickly say what is this Lagrangian approach. So the idea is you have a Liouville field phi, which is some boson, and you write a Lagrangian, which is d phi, d bar phi, plus mu e to the 2b phi. B is the same B that I had, is I beta, right? And mu is the cosmological constant. It's a very not important parameter. And then you identify your field Vp with exponential q plus 2ip So this is just an exponential, and this construction gives you a privileged normalization for Vp. I mean, you just take it to be the exponential without any prefactor. And so therefore, eventually you get some 3-point function with a certain normalization, which is in fact not my normalization, which I have here, C hat. So the C hat DOZZ, well, is just the same up to normalization. So you still have this factor, gamma beta, gamma b, sorry, 2 over 2. But you also get in the denominator a product I equals 1 to 3 of gamma b of 2i. No, let's say k equals I to 1 to 3, 2ipk, gamma b of q minus 2ipk. So in this new normalization, you lose, in fact, the invariance on the reflection. P goes to minus p. It's only covariant on the reflection. But essentially, that's the normalization which corresponds to this particular approach to Liouville theory. Okay, so to be sure, I mean, those DODD formulas, they are also prefactors which depend on mu, but they are not very important. And if you fix mu to some specific value, you can make these prefactors be trivial. Okay, so now there is, yes?
This view, what is it that we have one more? We seem to have one more parameter in the action than we do in the CFT in your presentation.
Yeah, so the point is this mu is not an important parameter. So already in the Lagrangian, you can see it because you can change mu by doing a constant shift of time. Okay. And eventually, there is a dependence on mu, but it is just some very trivial prefactor mu to some power, something like mu to the sum of alpha of pi, something like that. So essentially, you can just ignore it. Okay, so this DODD normalization is, well, it's not just some random normalization. It has an interesting property, which you can see already in this formula for the vertex operator in this approach, which is that if you set P equals P11, so the momentum of the identity field, well, so let me remind you, PRS is half of beta R minus beta minus 1s. And if you look carefully at what happens if P equals P11, you see that this number is 0. So you have B P11, 1. It's a Lagrangian approach. So the interpretation of that in the bootstrap approach is that the limit of P, when P goes to P11, should be the identity field, basically. Because 1, well, 1 is just some number which doesn't affect any correlation function if I insert it. So that's the same property as we have with the identity field. I mean, this is not a trivial property. I mean, we start with a field which corresponds to some Verma module. All the descendants form a Verma module, and then we are saying that if we just send its momentum to some value, it becomes degenerate. And in particular, we start with an OPE, which was, well, a continuous OPE, and then we are claiming that if in this limit, it should collapse to a very trivial OPE. So I'd like to give a small sketch of how this is possible. So we start with an OPE, let's say GP1, GP2 equals schematically integral GP CP1, P2, P, VP. And then we say P1 to P11. So we have to look at what happens in the structure constant now of the, well, the DODD structure constant, this one. And the first thing that happens is that you have in the denominator this gamma B function, and if P1 goes to P11, the corresponding gamma B function has a zero, has a pole, sorry. So therefore the C hat DODD goes to 0. So at first sight, it looks like the limit of this OP is just 0. Well, that's not the correct answer, as you can guess. So what's happening? Well, sorry?
It becomes some delta function.
Right. So what's happening is I exchanged the limit and the integral without looking in more detail, but I should look in more detail at the analytic properties of the integral. I mean, do they allow me to exchange the limit and the integral? And of course they don't. So what's happening now is that you have this line of integration over P, and you have to look at the poles now of this C, because now this C poles from this gamma B on the numerator. The position of poles depends on the various momentums, P1, P2, P3. And the point is that we have here some lattice of poles. Well, I'm taking B to be some generic complex number. And you also have lattice of poles there. You have lattice of poles both upstairs and downstairs because you have this P here comes with the two possible signs, plus or minus. And the position of this first pole here depends on P1. And basically, when P1 goes to P11, these two poles, they want to collide. And so basically, you can't exchange the integral with the limit, because in the limit, you have poles very close to the integration line. So in order to exchange them, what you have to do is to first make this pole cross the integration line. Well, you can do it by shifting your integration line, let's say, here. Well, you take it between this pole and the other pole upstairs. So you want to cross only one pole. And in the limit, you can stay here at a safe distance from all the poles. And now you can exchange the limit and the integral, and you get your zero. However, in the process of crossing the pole, you have fixed the residue. So what's left of this integral is just the residue. And then your limit becomes, let me write it here. So limit of the integral P1 to P is just the limit when P1 goes to P11 of the residue at the pole P equals P1 plus P2 minus P11 of the integrand, which is C1 to P VP. And if you compute this residue and compute this limit, what do you find?
VP.
Right, V2, V or VP2, depending on the notation. And so therefore, in the limit, you do have the correct fusion rule for the identity field. Which was not at all the case in Liouville theory with C less than 1, for example. In that case, the limit was just, the integral remained an integral, nothing much happened, and you, well, the limit of, I mean, let me write it. There. So C less than 1, the limit of VP when P goes to P11, when it was just VP11, some field which is diagonal but not degenerate and which happened to have dimension 0. And now for C generic in the DOZZ normalization, what you have, actually it works not just for P11, but for any degenerate momentum PRS, the limit of VP is a degenerate field. That's a remarkable property of Liouville theory.
In terms of fields, the battery why is VP on one?
But for C less than 1, you don't have a path integral. Well, people are working on it, but it's not easy.
I mean, you never used the fact that you could represent your V as exponential of free field. I mean, could it be useful to get results, or just?
Well, now that the theory is solved, I mean, I'm not sure it would be so useful. I mean, it would be useful to prove rigorously the solution, or it could be useful maybe to make contact with the lattice construction of Liouville theory. but it does not work so far.
What is the lattice construction of limit theory?
Well, we don't really know it, so people are working on it. You just ask Romain there what he thinks about it. I mean, with the bootstrap, we are constructing some, let's say, abstract CFT, but if you want to relate it to some statistical model or maybe string theory, yeah, it can be useful to have either path integral representation or lattice construction. For the moment, we just have the bootstrap solution. Okay, so that's Liouville theory. So I'm going to move to non-diagonal CFTs if there are no more questions. Oops, I'm again trying to erase my fundamental equation. Well, something like that. So now we have to solve the same equations here, but instead of taking all fields to be diagonal, we want some of them to be non-diagonal. So the next case is D-series minimal models or generalized D-series minimal models. So in this case, we have not only diagonal fields in the spectrum, but we also have non-diagonal fields with R S, with R some even integer and S some half integer. So in the case of D-series minimal models, these integers were bounded in some rectangle, which was a shifted cat table. So you had finitely many of these fields. And the generalized D-series minimal model is when you send the central chart to a generic value and you don't have a cat table anymore. So all these values are allowed in the generalized case. Now, what 3-point functions do we want to compute? So again, if you remember, due to the existence of the degenerate field V 2, 1, S, the second cat's index, was conserved modulo integers. And this implies in particular conservation of diagonality. So you have only two types of 3-point functions. Either you have 3 diagonal fields, or you have a diagonal with 2 non-diagonals. So this case is more or less under control. Well, you'll see that more or less doesn't mean really under control. But okay, let's start with the other case, which is the newest case. So you have 1 diagonal and 2 non-diagonal fields, and we want to solve this equation. And here, well, I just want to give you an ansatz for this solution. So P1, R2S2, R3S3 equals -1 to the R3 over 2 times a product again of gamma beta functions. So gamma beta -1 of beta plus beta -1 over 2 plus P1 plus minus P2 plus minus P3, gamma beta -1 of beta plus beta -1 over 2 minus P1 plus minus P2 bar plus minus P3 bar. So, okay, just an ansatz, which is a more or less natural generalization of what we had in the purely diagonal case. Except that now I have to distinguish P2 from P2 bar and P3 with P3 bar. And in particular, it looks like I've broken some symmetry here. So that P1 coincides with minus P1. I mean, from this formula, it's not obvious. But in fact, it is the case. You can prove it by some tedious calculation, but since this P2 and P2 bar, P3 and P3 bar, they have very specific indices. Here, it implies this equality. So the next question is, does it solve my fifth equations? And the answer is almost always. So the only equation that's not solved is the equation for P1 plus beta over 2 over 6p1 minus beta over 2. If you compute this from this on that, well, you find essentially this thing, which is what we want, modulo a minus sign. Okay, so that's just a claim. I hope it's plausible, but I mean, I don't have a simple way to argue for it except by doing the calculation. But that's really a calculation where you should pay attention to signs, because this sign will be very important. So what do we do with this sign? So now I want to focus on the D-series minimal model. So my VP1 is in fact a degenerate field here. So it should be some VR1 S1.
What is square root of minus 1 in your formula over there?
Which formula? There?
Yes, I mean,
No.
there you have an ambiguity of sign.
No. R3 is even integral
Ah, sorry. Okay.
in this spectrum.
Okay, sorry.
If we, I mean, we seem to follow the same calculation and we find the minus sign somehow. It's mysterious.
Yeah, so basically, to get this, you try to generalize the formula we had in Liouville theory. Okay, so you don't know how to, I mean, you have the distinction between P2 and P2 bars. So you just distribute them in different factors, the P and the P bars. But it's still a generalization of Liouville, the Liouville formula. And then, based on this natural answer, you just compute this ratio here and see if your equation is satisfied. Yeah, that's just the outcome of the calculation. Nasty sign. So,
Nearly there.
Hmm?
Nearly quite there, I mean.
Yeah.
So I find it, I would think I have made a mistake. But
Right, I mean, you think you made a mistake, and then you check everything, and in particular, you check the properties of this and the permutations of fields, and you check everything you can, and you find the sign is there. Now, we are no longer in a mistake-checking situation, we are in interpretations.
you want to check invariance under permutation.
Yeah, you have to make these checks.
So the claim is that that formula is invariant under permutation.
Well, not invariant, but it behaves as it should under permutations, basically. Because if you permute, I mean, the 3-point structure constant is not supposed to be invariant under permutations. If fields have spin, you could pick a minus sign under permutation. So you have to check it. I mean, in particular, this minus to the R3 is there for a reason. I mean, this breaks permutation invariance between 2 and 3, but precisely that's what you need in order to have the right sign if you do permutation while these fields have non-trivial spins.
Just to be sure, the fact that there is a minus sign means the formula is wrong.
Yes, yeah. We will have to fix it, right? Yeah.
Slightly wrong.
Slightly wrong, yeah. So almost correct. So if we're in the D-series minimal model, it's easy to fix. Because our fields, now they don't have continuous momentum, they have discrete momentum here, parameterized by integrals R1, S1. And in fact, we have R1 an odd integer. Well, 2n plus 1. So that's the spectrum of the D-series minimal model. If you remember, it's odd because we built the diagonal sector by fusion from the non-diagonal sector. And since R is even, always even in the non-diagonal sector, by degenerate fusion rules, this one is always odd. So now what we do is to change the normalization of this field. VD R1S1 to minus 1 to the R1 plus 1 over 2 VD R1 S2. And this sign precisely picks, this prefactor picks a minus sign whenever I do this type of ratios, because this ratio amounts to doing R1 goes to R1 plus 2. And so it eliminates our sign, and therefore our formula now becomes correct, because by doing this renormalization, I have slightly changed the shift equation by a sign precisely. And so I have solved them with this and that.
Is it equivalent to keeping all the fields what they are, but just multiplying the formula by the same sign?
Right, it's equivalent. But I want to do it that way because I want to push the signs to the diagonal sector instead of the non-diagonal sector, if you want. Indeed, so what happens now is if I consider a 3-point function of diagonal degenerate fields, so we already solved that. I mean, we know this should give us C, I mean, the same C as in Liouville theory applied to these degenerate values. So C PR1S1, PR2 S2, PR3 S3. But now that I have made this change of normalization, I'm getting an extra prefactor here as well, which is R1 plus R2 plus R3 plus 1 over 2, minus to this C. But that completes the solution of the D-series minimal model. So the non-diagonal structure constant is this one, and the diagonal structure constant is this one. And of course, if I wanted, I could avoid doing this thing, and then I would not get this sign, but I would get the sign over there. Now the trouble will start when going to the D-series, to the generalized D-series minimal model. Because now I have to do a limit of V R1S1 when P R1S1 goes to some arbitrary momentum P1. So in particular, if I try to apply this limit to this diagonal 3-point function, well, this T goes to the limit very easily. I get CP1, P2, P3. But this prefactor now, well, doesn't have a limit, right?
The prefactor, there is no +3 over 2.
Yeah, it should be +3, but it's equivalent. I mean, I can always multiply everything by a minus.
Okay.
All structure constants. But yeah, maybe I should have better like 3. Okay, so
This object limit kind of assumes that the BD exists for arbitrary. They can limit continuously.
yes. Well, okay. So you're first supposed to you at the same time you're sending beta squared to a non-rational value. So if you want, the cat table becomes infinite, and then you have access to any integer indices here. So that way you can reach any momentum, any real momentum in the limit.
So the reason you're saying it doesn't have a limit is because in this limit somehow R1, R2, R3 are becoming very large.
Right. Yeah, yeah. So what do we do? Well, when in doubt, just study an OPE. That's the general rule. So you should not study this as just isolated structure constant, but you should study it in the context of some OPE, like VP1, VP2 equals sum So originally in the minimal model, it's a discrete sum. So sum of R3, S3 of the structure constant we had there. So the sign times the C times some V R3, S3. Okay, so we start with the degenerate fields. And now we want to take the limit of these things and see how the right-hand side behaves. And if you do that, well, you get essentially that.
Why don't you pick the operator that lowers one of the indices, because it's not C, it's C with one of the.
Yeah, I'm going a bit fast there, but indeed you have an extra factor for lowering the indices, which does not really affect this particular issue. Okay, so if you do that, you find in the limit, you find in this some VP1, VP2 with arbitrary momentum, and you find, as you would expect, an integral here, an integral of the P3. There is a prefactor coming from this prefactor here, which is CP1, P2, P3, VP3, and you have an extra factor which essentially comes from this, which is a phi P1, P2, P3. And this phi is the following. So it is a beta, a sum of integer n minus 1 to the n product I equals 1 to 3 cos 2 pi n beta pi over cos pi n beta squared. So this factor, I mean, this sum over n does not converge. But it doesn't really matter, because what should converge is the sum after doing the integral. So in other words, the limit of this, and this phi is not a function, it's a distribution. So we get a slightly weird structure constant, which is not just discontinuous, but which is a distribution actually. But nevertheless, the OPE makes perfect sense, and the correlation functions make sense as well. So this is a solution of the CFT.
So what's the support of the distribution? What does it pick up?
Well, okay, the distribution has to be integrated against, if you want, whatever you have in the CFT. So if you're in a 4-point function, for example, you integrate against this type of structure constants times the conformal blocks. And it's the analytic behavior of these things, I mean, it's not that well known mathematically, I would say. But essentially, if you assume, I mean, this distribution, it's okay as long as you integrate it against something which decreases exponentially. Because for almost all values of beta squared, this thing will only blow up polynomially. So actually, you have a set of values of beta squared where it blows up faster than polynomial, which are called actually Liouville numbers, coincidentally. But these Liouville numbers, they are of measure 0. So if you assume you are not on a Liouville number, this does not blow up too fast, and you think that this integral converges.
Liouville number in the sense of having very quickly convergent rational approximation, is that the
right? Yeah. Yeah, Liouville is everywhere, apparently.
Why are we doing the bootstrap approach? Why are we not solving the D series first and then takes the limit?
Well, that's essentially what we are doing, right? I mean, we started to, we fully solved the D series, which was given by this solution, basically, this diagonal structure constant and this non-diagonal structure constant. And then I'm quickly describing what happens when you take the limit. Maybe that's a good point for a break before we move to loop models. So let's start again. So, so far we've been looking at conformal field series with two degenerate fields, two independent degenerate fields. So V21 and V12. And the fact we had these two fields was crucial for finding the exact solution. Because, for example, when you had a continuous momentum P, one field was giving you the shift by beta, the other field by beta inverse, and that was enough to essentially uniquely determine the solution. So in loop models, we have only one field. And obviously, this will not determine a unique solution. I mean, the analytic bootstrap we did so far will not determine a unique solution. And nevertheless, let's see what we can do. So we have a spectrum which is made of, well, we can have a priori diagonal fields here. We have some degenerate fields, and we have non-diagonal fields. And as a result of the existence of the degenerate field, we had constraints in R and S. So the first constraint was R half integral. Well, it was also a consequence of single valueness of correlation function. So R half integral with R conserved modulo integrals. And we wanted the field to be, let's say, half integral. So S had to be in 1 over 2 RZ. So you have correlation functions, well, 3-point functions of the type CR1S1, R2S2, R3S3. And in fact, okay, this will also include the case when some fields are diagonal, because you can consider a diagonal field as a VRS with R equals 0. So VP, if you want, is the same as V0 to beta P. Or equivalently, you can write V0S, V1 half beta minus 1S. So let's forget about diagonal fields since they will be included in the general case. And now we, a priori, want to use again our shift equations to constrain and determine these 3-point structure constants. So the shift equations will tell us, in fact, how they behave when Si goes to Si plus 2. But that's far from enough, because first, there is no constraint at all on the dependence on R, on the first cat index. And second, well, Si is actually fractional, so knowing how it behaves on the integral shifts is not enough. So what do we do? Well, the idea is to look for some solution of these shift equations, which is nice. And then when we have data, maybe numerical data from the bootstrap, we can compare them to this solution and hope that the ratio is not too complicated. Okay, so this is a bit vague as a plan, but I mean that's how we do so far until we have a better idea. So let's look for a simple enough solution. So we know that our solution will be a bit like that. It will be a product of gamma beta inverse functions. I mean, this is already a leap of faith, because this gamma beta, I mean, it appeared because it obeyed shift equation, and the gamma beta effect was defined by having nice behavior on the x goes to x plus beta and x goes to x plus beta minus 1. But now we only have one degenerate field, so we are only basically interested in this, and there's no real reason why our structure constant should be nice and the x goes to x plus beta. But okay, since that's what we know, let's go with it and see if it works. So let's try to write an ansatz now for this phi as some product of gamma beta inverse. So I wanted to reduce to the original Liouville 3-point function in the case when all the fields are diagonal. So in the case when R is 0. So to do that, it's not very hard. I can have here plus. So let me write the signs now as epsilon. Epsilon 1, epsilon 2, epsilon 3 equals plus minus. So I take here a beta minus 1 over 2 sum epsilon I S I. Okay, so this is a rewriting of my original Liouville. So Liouville was just the product of gamma beta of, I have plus or minus P1 plus minus P2 plus minus P3. So I'm just rewriting this now in terms of this S, because P is related to, I mean, P is 1/2 beta minus 1S. So now I have to make it also depend on R. So what could I do? So, do you have a guess? Well, okay. No guess. So let me make a guess then. Okay, so epsilon I L I. Okay, so nice guess. Okay, let me just put a minus sign here, but doesn't matter much. In fact, I could put a plus or a minus. The point, if I put a minus, this is the same essentially as this thing, where P, I mean, let me remind you that PRS half beta R minus beta minus 1S. So if I put a minus, I have this thing, but if I put a plus, I would get the same thing with P bars now. Right? So I have to decide between the P's and P bar. What is my preferred, the left or the right? I have to make a political choice, apparently. But actually, I want to stay apolitical in this course. So how do I write a formula that's neither left nor right?
Both left and right.
Or both left and right, if you want. Well, the thing is, okay, this R and S a priori are discrete variables. So I don't care much about analyticity. I don't want to write something like a function really of the momentum. So what I'm allowed to do, and what will be my ansatz, will be to have a plus and here an absolute value. So absolute values are apolitical, right? And okay, if I do that, I don't choose between left and right. It's just
You are abusing notation because your norm was defined differently.
And there's no square.
yeah, it's not a norm squared, it's only a norm. I mean, this one is a real, honest, absolute value without any tricky notation. But what's inside is a real number. Well, it's not even a real number. In fact, it's an integer number. Because R is conserved modulo integers. Okay, so let's see, this is the ansatz. So let me call it C ref for reference structure constant. I mean, it's really an ansatz. It will not turn out to be a 3-point function in loop models. But it's something I can compare any 3-point function with. So now the claim, I mean, is that at least it should solve the shift equations, which I have, and which should determine its behavior on the S raised to S plus 2. So again, that's a claim I will leave to as an exercise. So check that this solves the shift equation. In fact, it's not quite true. It's up to sign. So when you take the shift equation of that, so C ref, let's say S1 plus 2 over C ref S1, you find well, what you want times, well, some sign. The sign depends on all these variables, but it's not, well, it's not a big problem. I'm not writing a physical 3-point function, I'm just writing a reference object. And okay, so if it solves the shift equations of two signs, it means that the true 3-point function will be, so the C has to be C ref times something which is invariant on the shift, right? So what does it mean to be invariant on the shift? Well, if I'm considering some diagonal field, so the shift equation for a diagonal field determines the behavior of the P goes to P plus beta inverse. So what is invariant on the P under this shift? Well, anything that's periodic. So in particular, let me define W of P equals 2 cos 2 pi beta P. I'm taking a cos here because I also want it to be reflection symmetric. W of P is W of minus P. So the physical structure constant has to be a C ref times some function of whatever P I have, if some of the fields are diagonal. Sorry, of W, a function of W of P. So W of P, for some reason, I'm calling it the loop weight. And then this function, well, it can also depend, of course, on beta squared, on the central charge via beta squared. However, it turns out that there is a combination, a special function of beta squared which appears there, which is W of P11. So if I'm taking the momentum of the identity field, P11, I mean, that's minus 2 cos pi beta squared. And let me call this N. And in the last course, I plan to show that this is the same N as in the ON model. So this would be the contractible loop weight. And so the claim is that this function depends on the central charge, but only via N now. And the even stronger claim is that this function f is a polynomial. So now I don't really have a good justification for this claim because it emerges basically from a numerical experiment by numerically solving the crossing symmetry. But yeah, of course, it helps us a lot find this structure constant.
Does it also take care of the signs in the shift equation?
Yeah, this f includes the whatever signs you need. Yes.
At least, I mean, there should be a comparison with the lattice model somehow. I mean, at some point.
Right. I mean, we're working on it. But originally, this results emerged from the numerical bootstrap. But indeed, I mean, in fact, we started to work on the lattice model in the case of 4-point functions. So that's already in an article last November. That this type of polynomials in 4-point functions, you can recover some of them from the lattice calculations. But now we are working on 3-point functions also.
Is there any idea of the degree of the polynomial? I mean,
yes, there is an idea of these degrees, which is crucial because I mean, if I tell you that you have to fit your numerical results with a polynomial of a degree at 21,000 something, then it's not very useful. So, but the degree is also a conjecture based on numerical results, right? We have seen patterns in the degrees of this polynomial. Basically, the degree depends on the R, the first cat indices. Well, they are simple functions of R, so they grow with R. So they are not so high. So in practice, we can get the polynomial. And there is also the notion that the coefficients of the polynomials are not just any numbers, but they are typically rational or trigonometric numbers. But in the last course, I plan to give some examples of polynomials of this type. But for the moment, we are not yet there. So for the moment, I think we are done with basically the analytic bootstrap. So what we can say from this idea of using degenerate fields and constraining our structure constants. And I want to say a few words about the numerical bootstrap before focusing more precisely on the correlation functions in loop models. So numerical bootstrap is a rather technical subject, so I will be very skeptical here. So why do we need the numerical bootstrap? So in principle, what we've done so far is based on using crossing symmetry for some very special 4-point functions involving degenerate fields. But if you want to show that your CFT exists, you have to show crossing symmetry for arbitrary 4-point functions, which so far we've not done at all. So basically, the 3-point structure constant for Liouville theory is unique based on this type of analytic bootstrap. It's unique, but so Liouville theory is unique, but we don't yet know if it exists. Well, there exist analytic approaches to crossing symmetry. So let me very briefly say the status of that. So these analytic approaches are basically based on building your CFT as some kind of perturbed free bosonic CFT, which in 2 dimensions, even though it's perturbative, it also gives you exact results. Because if you do that, you're building your 4-point function as some object, not in any given channel, just some object, and then what you have to show is that you can decompose it into conformal blocks in any channel. So you have if you want some object which is already crossing symmetric, but you still want to decompose it. So there are several of these approaches. So the first one historically is the Dotsenko-Faddeev integral, which works in minimal models. So basically, you write your 4-point functions as integral with a large number of variables. Number of variables depend on the particular 4-point function you're considering. So you have your 4-point function, you take some integral over the complex plane. Well, here I'm writing just one variable for simplicity. And then you have to decompose it into blocks. So you do that by essentially writing this integral as a product of contour integrals. So if you want to have a left contour times the right contour. And then you pick some structure constant here, and you get a sum, and that's your decomposition into conformal blocks.
So it's like 2 chiral theories, but you take linear combinations.
Yeah, right. So in this approach, you view that as a decomposing some complex integral into contour integrals. So that works for minimal models, but it wouldn't work for Liouville theory, for example, or not generically, maybe in some special 4-point function in Liouville theory, but not for all 4-point functions. So in Liouville theory, you need to do something more complicated, and you can build Liouville theory as some perturbed free boson in a vertex operator algebra approach. And that's what Teschner basically has been doing. So this is one way basically of making sense of some exponential of your free field. So the challenge is to make sense of this type of expressions. I mean, because when you have a field here, it's already not obvious how to make a product of fields, because fields typically are distributions, and then you even want to exponential. And there's another way to do that, which is to some probabilistic approach. So this approach involves mathematicians. It's much more recent, and apparently it's well, very rigorous and fashionable these days. Yeah, for me, the advantage of the probabilistic approach is that, well, it's probabilistic, so probabilities have to be real or even positive numbers. And if you insist on having positive numbers, well, you can say goodbye to everything that's complex analysis. well, I'm caricaturing a bit. I mean, in fact, they can recover some properties of complex analyticity, maybe not in the central charge, but in the momentums at least. But that's, like, I would say, not very natural.
Harmonic analysis can be very close to probability. I mean, you can Brownian motion in 2D. I guess it uses this kind of arguments.
Yeah. But okay, so far they have restrictions on the central charge. I mean, I think the central charge has to be real, and I'm not sure it even works for C less than 1. The safe place for them is C more than 25. Okay, so these are like exact approaches to proving crossing symmetry, but it's simpler just to take a computer and compute your 4-point functions. Now that we know the structure constants, I mean, you can do numerical checks, and if it works to 50 digits, then that's pretty convincing, I would say. And you don't have any restriction on the values of parameters. Now you can take complex central charge all you want.
You need also the conformal blocks.
Right, you need to compute conformal blocks, which I won't talk about, but in fact you can compute conformal blocks to any accuracy. So let me sketch what happens when you want to solve a numerically crossing symmetry. So crossing symmetry, let me remind you, is the equality between S and P channel. So you have S channel structure constant. So you sum over the S channel spectrum, sorry, S, you sum structure constant times some conformal blocks, D delta K S. And you want this to be equal to the same in the T channel. So here I'm assuming that we know the spectrums of conformal dimension ST and SS. Of course, you can also use this equation to constrain the spectrum, but that's much harder. And typically, to do that, you need some extra assumptions like unitarity to make things positive. So here I'm assuming we know exactly the spectrum. So the unknowns are only the structure constants here, the 4-point structure constants, and we have a linear equation, 4-point structure constants. Well, they can be normalized, like you can assume that for some value of the label k, some structure constant is 1, so this normalizes things, and hopefully the solution can be unique. But is it always unique? So that's what we will now discuss. So let's assume we have some 4-point function, and we want to solve these crossing symmetry equations. Well, to start with, we have to truncate them. I mean, typically these are infinite sums, so you put some truncation there, and you get some solutions. And then what you do is you see if how this solution evolves when your cutoff becomes very large. And if the solution is stable, then you consider that you have a good numerical solution. Yeah, maybe I was a bit quick. I mean, I want to say this is an equation for infinitely many unknowns. So the decay with k belongs to the spectrum, which is typically infinite. But you also have infinitely many equations because these blocks depend on z. So you can take any complex value of z, the cross ratio that you want. Yeah, but of course, numerically, you truncate it to a finite system. But you have to see how the system behaves when the size grows.
It's a linear system. Non, c'est des équations linéaires.
Yeah, here this is the linear equation for dk. And there's a question about the spin. Yeah, so delta k now means the left and the right dimensions. But I'm writing delta k just to emphasize that the blocks depend just on the dimension, not on this label directly. Okay, so
if you solve for decay for these, it's not necessarily guaranteed that you can recover the 3-point function because these are themselves kind of bilinear.
Right, I was going to discuss that a bit later. So for the moment, I want to discuss this linear system, but then indeed we have to recover the seed. But first, this linear system. So the first question is, do you know the structure constants? so the decay. So do you already know the solutions? Well, this happens, for example, in Liouville theory. Liouville theory or in minimal model, you know the solution. And then what's left is to check that this is obeyed. And you just check. And this allows you to check crossing symmetry, for example, well, in Liouville, generalized minimal models, Runkel-Watts type CFTs, or DC with minimal models, or generalized DC with minimal models. In all of this, you can check numerically crossing symmetry. Now, the other option is that you don't already know the structure constants, so then you want to determine them. And the question is to find the solution of this system. Well, maybe you don't find any solution. What do you conclude? Well, probably your spectrum is wrong. So you have to modify the spectrum and try again. But let's assume we find solutions. Then there are other options, other possibilities. Because the question is whether the solution you find is unique. So it could be that the solution is not unique, but then what you can do is to find the number of solutions, or if you want the dimension of the space of solutions, which is in loop models at least finite dimensional. So you compute just numbers of solutions. Yeah, this can be done in loop model or in the ON, Potts model, etc. If the solution now is unique, well, first you conclude that your spectrum was correct, or at least that it's consistent, that it gives you nice 4-point function. Then, if you want, you can compute the 4-point function. So, because you have now you know the solution to some precision, and you compute this 4-point function. And if you're interested in comparing with like Monte Carlo or any other approach, the lattice, you can do that. So that we have. I mean, it has been done a lot for connectivities in the Potts model. In fact, so there are particular observables, cluster connectivities, and a few years ago we were busy comparing numerical bootstrap results with Monte Carlo or other results for connectivities. And finally, if you have a good numerical determination of the structure constants, you can try to find an exact formula for this results, and that's where it becomes useful that you have an ansatz, so this reference structure constants, to which you compare your numerical results. Okay, so that's all I want to say a priori on this linear system. And now there remains the question, indeed, of factorizing the 4-point structure constants. For example, in the channel, in terms of, well, 3-point structure constants, something like C1 to K, CK, C4.
Sorry, for which values of Z the series converge on both sides?
So
do you have an a priori?
Right, so no, it should converge for any value of Z. Any complex value of Z, except that it becomes, I mean, the blocks become singular, typically when Z equals 0, 1, or infinity, which means when 2 of the 4 fields coincide. So you want to stay a bit far from these values, but otherwise you
ask for the, okay.
It does not simplify, at the contrary, when Z is very close to one of these points.
Well, it simplifies in the S channel if you want. If Z close to 0, in the S channel is just dominated by the ground state, but it's more complicated for the other channels. So you don't want to favor one channel over the others. When you do the numerics, typically you take Z to be a bit far from all these singularities.
And I have another question. When you do not have the same number of, like when the solution is not unique, does the number of solutions depend on the?
depend on Z.
I mean, a priori, I check Z equal 1/2. I found 10 solution. I check Z equal 1/3. I found
No,
11 solutions.
No, it doesn't work exactly like this, in fact, because anyway you have to take several values of Z. So you define your system as all these equations for any Z, basically. So what I call a solution is something such that these equations are made for any Z. But to know I have a solution, let's say, I have to solve this system. Let's say you want to compute 30 structure constants. So K can take 30 different values. Then maybe you take 30 values of Z to get a solution. And then you have to check if this solution is still a solution when you take another value of Z, which is outside the first 30. So you take a 31st value, and that's how you evaluate basically if this was a good solution.
And typically, you have the same number of solutions. You find typically the same number of solutions, or it happens that you have spurious solutions that are there for some bunch of values of Z, or
no. Really, almost by definition, the number of solutions does not depend on your choice of values of Z.
Okay.
If you find something depending on that, you conclude it's not really a solution. If you want spurious solutions, what you can do is, in fact, to solve these equations and not worry about the U channel, because in principle, this should also coincide with U channel, the U channel sum, and in practice, we are solving the equality between the 3 channels. If you do only 2 channels, then you can find some spurious solutions.
Okay.
Okay, so now we have the 4-point structure constants. So how do we decompose them into 3-point structure constants? So a priori, you could think it's an easy problem. You just vary the field 1 and 2 or the field 3 and 4 and see if your V factorizes. The difficulty is that it does not have to factorize in general, because you could have several fields with the same dimension. So what the bootstrap gives you is not really the decay, but the bootstrap gives you the coefficient of a given block G. And the coefficient of a given block of a given dimension is in fact not decay, but it's the sum of decay for all K, for all fields which have a given dimension. So the left dimension delta K and the right dimension delta K. So what the bootstrap gives you then is a priori not factorized. It's a sum of factorized terms. And you don't a priori know how many terms. And well, if you take any function, you allow infinitely many terms, you can always factorize it. So here you have to look for factorization in terms of 1 term, or maybe 2 terms or 3 terms, and see if you can find a factorization with few terms. But if you can never prove it, it will not factorize.
In the loop models, are there points in the end space where the spectrum is simple? The spectrum has no multiplicity?
Well, it's a very subtle question, because I mean we don't really know how to define multiplicities in the loop model so far. What we can do is to look at some results for some 4-point structure constants and see if they factorize. And so far, all the results factorize into finitely many terms, but we don't have an understanding of these terms.
Potts model, it could be related to some kind of symmetry or something.
Right. So in the Potts and ON models, there is a natural definition of multiplicity, which is related indeed to the global symmetry, to the ON or the SQ symmetry. But the problem with that is that it gives you very high multiplicities. It would predict the number of terms which is basically too high, and which in the numerical results you don't have that many terms.
I guess you want to work with not individual operators, but with the arrays themselves.
Right, but even if you do that, you typically find too many terms, except in very simple cases.
So the status of the spectrum of the ON model is that it's not really known at the moment. Even the spectrum.
But we know how it decomposes into representations of the conformal symmetry and also into representations of OM. But we think it's not a good way to describe it. Because OM symmetry gives you a very redundant description of the model. But I can say a bit more when I talk next time about correlation functions. Okay, so in practice, in your bootstrap calculations, you have this problem, and well, there is a practical way to solve this problem, right? You put your structure constants in a big matrix. So basically, you write this D. So now D, let's call it D delta delta bar. So the structure constant associated to some left and right dimensions. So you put D delta delta bar in a matrix where you vary the 4-point functions D1, D2, D3, D4. So either you vary the field 1 and 2, or you vary the fields 3 and 4. So you vary the field 1 and 2 in one direction of the matrix, let's say for the for the rows, and you vary 3 and 4 in the columns of the matrix. And you want to compute the rank of this matrix. And that's what you would call the multiplicity of the field with dimensions delta delta bar. So in principle, it's an infinite matrix, but you can take finite submatrices and look at their rank. And I mean, if the big matrix is of finite rank, you will see that all these submatrices basically have the same rank or lower. And numerically, we can determine this.
Can you compute this reliably if you only know D to some numerical precision?
Yeah, that's a good question, because to compute the rank, you have to show that some determinants vanish, and you have to say numerically what it means to vanish. So it's a bit tricky, but I would say that it can be done, at least in some examples. Okay, so that's all I can sketch about the numerical bootstrap without getting into technical details. So, are there any other questions on this numerical bootstrap? So, if not, I propose to talk about correlation functions in loop models. And here, this will be the only place in the course where I will leave the bootstrap approach, basically. So I want to talk about the loop models as statistical models. I need to do that because, in particular, to motivate the introduction of combinatorial maps. Because combinatorial maps are objects which will eventually parameterize the correlation functions in loop models, which will parameterize solutions of crossing symmetry. But I don't know an intuitive way to introduce them just from the bootstrap alone. So that's why I want to talk about the statistical model. But I also don't want to get into the details like transfer matrix and technical details. So I will talk about the statistical models in a very general way. But you're free to protest if things are too vague, because they can be made more precise. I hope we don't need to get into too much detail. So what is a loop model? Well, first, what is a statistical model? So let's define some partition function depending on some ensemble E. As a sum for some configurations belonging to the ensemble of some weight, the weight of the configuration. So this partition function, in some critical limit, is supposed to correspond to some correlation function in our CFT. So in loop models, what are these configurations? Well, they are configurations of loops. So E is some ensemble of loops. So you have several ways to define ensembles of loops. So one simple way is on some lattice. So let's take some finite lattice here. And on the lattice, you can decide if its edge is occupied or not. and such that you form some loops. Well, this is one loop on the lattice. Well, you could have a loop here which comes close but does not really touch it, so some other loop, and etc. You can have. So there are a lot of different loop models depending on what rules you adopt for drawing these loops. So, for example, you can assume that all vertices must be visited by some loop, so this makes a very dense model. Or you could assume that any edge must be visited, which is slightly different. You can take a square lattice, you can take a hexagonal lattice, you can take a random lattice, you can do all kinds of things. But so, for me, I mean, it will not really matter. I mean, anyway, many of these differences get erased in the critical limit, and by universality, you end up in not too many different CFTs.
Perhaps your loop model must be critical. I mean, it could be massive.
Right. I mean, to get a CFT, I'm assuming it has a critical limit. So, the nice thing about the lattice is that everything is finite. So the number of configurations is finite, and each configuration is finite, meaning you have finitely many loops in the configuration. But there are other ways to define these loops, because I mean, the big problem with the lattice is that you manifestly break conformal symmetry. So then you have to recover conformal symmetry in the critical limit. However, you can define a conformal loop ensemble. So this is work by mathematicians, I mean probabilists, where you define some loops here without any lattice, basically. And from the start, you have conformal symmetry. The problem, however, is that you have infinitely many configurations, and I think even infinitely many loops per configuration. So I will be a bit agnostic about this, and I will just assume that I have some ensemble of loops with finitely many loops in each configuration. And then I want to define the weight of the configuration. And one simple on that is that the weight is extensive. So you have a certain weight for each loop. And each loop has weight n. And you put n to the number of loops. And that's it. That's your weight.
I think it's shouldn't you address the weight of the loop?
Well, I mean, it depends a bit. I mean, in the dense phase of the ON model, I think you don't have much to adjust. I mean, you have a coupling, but you have a range of values of couplings where it's critical. You don't have really to fine-tune the coupling. But in the dilute phase, you have to fine-tune the coupling. So I don't get into these details, but what I want is to introduce this parameter n, because this will eventually be related to the CFT, whereas the coupling itself is not universal. And in fact, this n is also the n of the ON model, if you want, or UN model. And it's because this loop model is a reformulation by Fortuyn and Castellane, basically, of a model of spins on your lattice. So at each side of your lattice, you have some spin, let's say Si, which is a vector with n dimensions, which so you would say it belongs to the fundamental representation of ON. And so there is a way to compute this sum, which eliminates the spins and replaces them with loops. And you get the n here because n is basically the dimension of this representation. But the nice thing about the loop formulation is that now n can be any complex number. Whereas here it has to be integral. So,
There's no difference between ON and UN?
yeah, there is in UN you would need S to be complex, and in ON it's real.
Yes, but I mean, from the loop model, you just write n to the.
Yeah, essentially that's the only difference. Well, I think so. Paul can contradict me if I'm wrong, but at this stage is the only difference. But it leads to important subtleties.
The question is, what is the difference from a loop model point of view between O1 and U1? Because the partition function doesn't depend on it.
No, in fact, the thing is, now you have, in UN you have orientable loops, loop configurations, instead of unoriented configurations. You want only configurations such that you can orient each loop such that neighboring loops have opposite orientations. And you need that. That comes from the UN symmetry, because basically in UN you have the fundamental and anti-fundamental representations which are different. And you identify them with two orientations for loops. Okay. Now, okay, so far we have defined some rather boring quantity which depends only on n, and therefore it corresponds to the partition function of our CFT, to a 0-point function, basically. So now we have to do something more to get non-trivial correlation functions. So let's introduce some punctures here. So I want to introduce punctures, but I don't want to break conformal symmetry eventually. And so the weight of the loops can depend on how loops are positioned with respect to this puncture. Like if a loop goes around this puncture, I could decide it has a different weight. However, if I want to preserve conformal symmetry, I mean, the weight, for example, cannot really depend on the shape of the puncture. It can only depend on which punctures are inside or outside a given loop. Sorry, I mean not the shape of the puncture, I mean the shape of the loop. So these two loops here, I can decide they have another weight. Instead of weight n, they will have some weight, let's say W3, if this is the puncture number 3. So how many different loop weights do you think I have in this configuration with 4 punctures? So you're saying that's a 4 factorial?
Une boucle, 2 boucles contre ces facteurs.
Well, in fact, it could be infinite if you think about it. Because yeah, you can look at the homotopy of this configuration, and in fact, you have infinitely many topologically different loops. For example, let me draw 2 loops around points 1 and 2. This one here, this configuration, this loop is different topologically from this loop, right? However, I want them to have the same weight because of an extra assumption, which is single valuedness. So I want eventually my statistical sum to be related to a single valued correlation function. And if it's single valued, it means that I can take this point and drag it around here and come back there, and the result will not change. And therefore, the weight of these 2 loops have to be the same. And that's why, in fact, I have only finitely many possible weights, because the weights are not topological objects, but they are combinatorial objects. I don't care what is the trajectory of my loop, I just care what's inside and what's outside. And even so, I don't even distinguish between inside and outside. So this I would call a S loop with a weight WS, because it goes around 1 and 2, or equivalently 3 and 4. So
No, it's the same because it goes around infinity.
That's what you said.
yeah, I'm saying this is the same weight, because combinatorially these 2 loops are the same with weight WS.
And you also say that it's the same as going around the 2 other points.
Yes, right. This is the same because we are on the sphere, so this is also weight WS.
Just to be sure, do you allow self-dissection in the loop or not?
No. So that's the basic assumption, which I forgot to say explicitly. Loops do not intersect. either with other loops or with themselves. So no.
Will still be infinite. Really.
So now, how many different loops do I have? How many different weights? Well, let me draw all of them. So when you have contractible loops with weight n, when you have loops with weight W1, sorry, that was 2, W3, W1, W4, and then I have S loops, WS, I have U loops, WU, and I have T loops, WT, and that's all. So in general, for n point function, you have 2 to the n minus 1 weight. Okay, and this weight a priori is just any complex number. So you get a continuous parameter which we are tempted to identify with the momentum of some diagonal field. So that's what we'll do next time. For the moment, I want to tell you about other types of functions that could exist. Because, I mean, we also have fields with discrete parameters, I mean the non-diagonal fields. So we have to do something more to get them. So what we can do is to have loops ending at some functions. Oh, now these functions, I want to draw them as circles to distinguish them from the other ones I have. So I could have things like that. Right? I mean, that's still, I'm still not breaking conformal symmetry by doing that. I mean, so my configuration now is not made only of closed loops, but also of open loops. But as for a vertex, a given vertex, I'm specifying how many open loops can end there. By definition, I call this number 2R, which has to be integer.
Sorry, I really don't understand why the loop which loops around the 1 and 3 does not have a weight which is W13.
Well, I just called it WU, but you could
No, but I mean, then I expect also W23 and another weight W23. If you have a loop that
no, but that's WT now. Around 2 and 3 is the same as around 1 and 4, and that's WT.
C'est sur une sphère, alors tu peux
because you deform them. Okay.
It's on the sphere.
Okay.
But you're right. I mean, if I was not on the sphere, I could have more weight.
Okay.
Yes.
Sorry. So if we start from the lattice model and we allow, for example, we relax some of the assumptions like no intersections, or we give different weights to topologically different loops now around the insertions. Does this mean that when we go to, let's say, to the critical temperature, what happens? Do you still have that the correlation length becomes infinite, but then you cannot have a CFT, or? Like...
I think the answer depends on the specifics now. But what happens if you allow intersections, it becomes much more complicated, and it's much less well known, I think. And
lattice, like you cannot just. It's difficult to actually simulate it even, or.
Yes, it's more difficult. And okay, I'm not the expert on the lattice side, but I mean, it's not just
the loops would be closed random walks. They are very well understood, in fact. Isn't it?
The point is,
avoiding objects are much more complicated than intersecting objects in general.
But I view intersecting objects as allowing more things, and each time you allow something, you have to add parameters if you want.
Sure.
So there could be indeed there could be intersecting objects that are very simple. If, for example, the weights don't depend on anything except maybe the number of loops. But what happens on your lattice model is that for each vertex you can have, well, if, for example, you have non-intersecting loops, then on each vertex, well, there are not so many things that can happen, right? Either this or that, assuming all edges are filled. But if you allow intersection, you get extra possibilities, like a possibility like this, and each extra possibility comes with an extra parameter and with more complications.
I have a related question. So, if we turn on these parameters, the W1, W2, and so on, corresponds to the local operator, should I think of it as defining a new model, or is it the same model with insertion of some local operators? Like, is the local dynamics the same? The critical temperature is the same, or no?
Yeah, the local dynamics is the same. So we will see it will give rise to the same CFT, basically, to another correlation function in the same CFT.
It's a 4-point function.
Yeah, here this will end up corresponding to a 4-point function. Well, to the 4-point function which we wrote as VP1, VP2, VP3, VP4.
From the point of view to explain it, it looks like you're modifying the Hamiltonian, but you're not really modifying the. You're somehow just inserting local.
I want to insert local operators.
But somehow it doesn't depend on these extra weights.
No, it does. Quick exploit. The S.
It's the momentum, I see.
This P1 will be related to W1.
I see.
The non-trivial question is what does WS correspond to in this?
Yeah.
So in the bootstrap approach, when you solve crossing symmetry, it's clear that WS corresponds to the weight of some field, to the momentum of some field which can propagate in the S channel. But from the point of view of CFT, obeying the CFT action, it's less clear because this 4-point function is only supposed to depend on these 4 fields and not on some extra parameters. And so for the moment, the conjecture is that if you have a dependence on WS, it means that you have some combinatorial defect here going along these 2 points. So it would not be really a 4-point function, just a 4-point function of primary fields, but you would have it would be in the presence of some defects. Okay. So let me come back to trying to introduce punctures where loops can end, so open loops. And a puncture is characterized first of all by the number of loops that end there, which I perversely decide to call 2R. But this is because I eventually want this R to be related to the first Katz index. And in fact, I already get a very nice result, which is that in any loop configuration, the sum of the R will be some integer, because I have to connect all my open loops with some other open loop. And now, what about the weight of the configuration? I mean, does it depend on these open loops? And that's where things become maybe a bit more subtle. The point is that I can do anything provided I don't break conformal symmetry. And by definition, conformal symmetry is the conformal transformation preserves angles. And here, if I come near this point, well, I can define angles. I mean, the angles of all these loops coming to the point. Or at least I can define these angles in my drawing. Because in any realistic loop model, the loops are not at all smooth like that. The loops are fractal. So it suddenly becomes much more difficult to define the angle. So here I'm making the big assumption that these angles make sense. I mean, I don't claim they make sense for any given loop in a given configuration, but I want them to make sense in the sense of this big sum of all configurations, in the sense that this big sum will have a well-defined limit. So to do that, I mean, if you're in a lattice, for example, you can try to define angles at a certain distance from your vertex. So some distance r, which you take much bigger than the lattice size. So you have really many lattice sites inside this radius, but this r should also be much smaller than the size of the overall lattice. So the lattice should go on much farther, and especially other vertices should be outside this circle. And then maybe I define the angles by intercepting my loops at on this circle. So that's one conjectural way to define the angles. So then if you accept that I can define angles, then the loop weights can depend on these angles. Which dependent can this be? So let's have a weight function associated to this vertex. Well, the weight function will be essentially the sum of the angles with some angular momentum S. Sum of theta. So let me now define more precisely what I mean by the theta. Okay, so thetas are in fact not the angles between the loops as I was suggesting here. So I want to define them a bit differently. So I have a number of loops ending there. So to measure angles, I need some reference direction, which I can take arbitrarily. So let's have a reference direction here. And then I also want a reference loop. So let's say this is the reference loop. So in my loop configuration, it's usually possible to define a reference loop just by saying maybe this is the loop, so this is point 1, maybe this is the loop that ends at puncture 2. Or maybe if I have several loops that end at puncture 2, I would say this is the last one, the last one clockwise, for example. So I can define a reference loop at this vertex. And then I define the angles as measured from the reference direction. So I define the angle here of, let's say it's called the 1. So theta 1 is just the angle for the reference loop, and theta 1 is in 0 to pi. Then the other theta k, I define it such that it belongs to theta 1 plus 2 pi. So the point of having this reference loop and of doing that is that now I'm not allowed, I mean, it's not that each weight, that each angle is defined modulo 2 pi. I don't have the right to shift my angle theta k by 2 pi. The only thing I can do is to shift all the angles by 2 pi. So theta k goes to theta k plus 2 pi for all k is allowed. And I want the weight to be invariant under such redefinitions of angles. And this implies that RS has to be integrated.
Maybe it's clear, but I don't see it. How dependent is this weight on the choices you made of references?
Right. So if you now define slightly differently your reference direction, each angle will change, but the point is that you get your W of E is multiplied by some phase factor, but the phase factor is the same for any configuration E. Right, so you factor it out of your big sum there, and it's not important.
Okay, so you have to change those cuts in the same way for all vertices.
No, you can do it for each vertex, in fact.
Independent.
Right.
Oh yeah, because all vertices contribute to any configuration. Okay. Yes.
Sorry, you didn't really say what are theta k for k different from 1.
It was supposed to define here. So theta k is an angle. It's also measured from this reference direction, but it's in this window of size 2 pi. It has to be bigger than theta 1.
They start from the reference. Okay.
Yeah.
What is anything that is RS? Okay, fine.
Right. So with this definition, I have allowed momentums, angular momentums, which are all the rational numbers so that RS is integer.
we define some other local operators which depend on the theta in a more complicated way than just the sum of it. I mean, it seems like a very special choice that it only depends on the sum of the theta.
Right, but I think that's pretty much all you can do if you want to have conformal symmetry in the limit. I mean, it has to be extensive. It's a bit like the loop weights. You have n to the number of loops. So each loop comes with a weight n. And thus, in the same way, each strand comes with a factor in this weight here. So it has to be exponential something. It has to be multiplicative. And I think that's pretty much the only thing you can do. Okay, so eventually, using all these weights, we get a V now, which is a sum of configurations of, well, of all the weights I have. So I have a product over the punctures. Let's call them I, product over I of some W. So now the punctures are labeled by Ri and Si. And each puncture associates some weight over there to some which configuration of loops. And then I have a product over closed loops of the corresponding weight factors. The only thing I've not said is which ensemble I sum over. Because now I have a number of punctures with some valency. So valency means the number of lines that should end there. And so let's assume, for instance, that I have a configuration here, a trivalent puncture, one valent and two valent. Now, without breaking conformal symmetry, I can specify basically which puncture is connected to which other puncture. And this data is called the combinatorial map. And so my sum will depend on the choice of a combinatorial map. And the set of configurations also depends on this map M. So the exercise now is how many combinatorial
You
maps?
start connecting the points together, then there are no loops which surround the points. I mean,
Right, exactly. So these loops where these punctures where open loops end, they don't have any loops surrounding them. They are different from the punctures like this where the loops go around. So the question is how many combinatorial maps exist in this case, in this example. So does anyone have an idea? Is it just a few? Just a few. That's a good answer already. So how many? Well, I can draw them. So one of them is certainly this one. Okay. Another one is this one. I also have this one. And I also have, I mean, nobody said they have to be connected, so I can do that as well. So I have 4 combinatorial maps here in this case.
Those are the really trivial loops. Okay.
Right.
That's why it's going to a point.
Exactly. So I'm forbidding things like this one, for example. This one. So this loop, which could be pulled inside the point.
So they do count as one valent.
Exactly. So this loop, I would say, can detach from the vertex and live its own life. So it doesn't count as it doesn't.
Even n is the weight of a loop, a standard weight. So this one wouldn't count.
Well, okay, yeah, it would count as n, indeed. But I mean, it doesn't count in your enumeration of possible maps, of possible combinatorial maps. But indeed, as a loop, it counts in the partition function. And okay, let me point out that for example, these maps are really combinatorial, so they are not topological. For example, here I could draw this one, but these two are in fact the same, because the same vertices are related in the same way. I don't care if this goes there, because again, I want the correlation functions to be single valued, so they should have no monodromy. And this one, from this one to this one, you go by doing some monodromy around another point. If I was allowing, if I was counting them differently, I would have infinitely many maps, in fact, but I don't, because my correlation functions should be single valued. Okay.
The maps without this restriction that you can move like that, aren't they counted by some matrix model and are they finite?
Well, if you don't, I mean, if you can, you mean the my combinatorial maps? Are they counted?
No, the other ones. I mean, the ones where you don't impose this.
If I don't identify them, I can draw infinitely many, because I could go around it infinitely many tags, right? I could do this probably. Right. But here, indeed, with my combinatorial definition, well, it's not my definition, but okay, a number of combinatorial maps is finite, and you have papers about counting them. So
It's matrix models, isn't it?
I'm not sure they use matrix models, but since everything is related to matrix models, probably it can be done.
They do very much like what people call maps when they do quantum gravity with matrix models, isn't it?
Well, maybe we can discuss it later.
Does this configuration come with extra weight? Like, I mean, you are surrounding a puncture, right? You are surrounding some of the part of.
You mean this one? The fact that no, the point is here my weights are only the ones I wrote here. So a local weight at each vertex, depending on the angles, and weight for each closed loop. Because okay, there are plenty of closed loops around there, of course, which I didn't draw. But you have closed loops there, closed loops there, closed loops there. So for example, in this map allows you to have closed loops of weight W4, WS, so S channel loop here, and N, of course, the contractible loop. So depending on the map, you can have a number of possible closed loops. So yeah, that's it. And the last thing maybe I want to say is how this is related to the ON and UN and POTS model very quickly. I was already sketching it before, but in the ON model, basically you want to allow all possible punctures of this type, so all loop-ending punctures. But then you want to say that all closed loops have the same weights, have the weight n. Then you have the UN model, and in the UN model, you want your loops configuration to be orientable, and another way of saying that is that your full space should be colorable. So in particular, near the vertex, we should be able to color it like that with different colors in all contiguous regions. And so you have in this model the restriction that R now is an integer. The valency of any vertex has to be even. And then in the POTS model, where the POTS model is a slightly more complicated variant of the UN model. So if anyone is interested in this particular case, we can discuss it. But the subtlety in the POTS model is that you don't want to define loops, but you want to put clusters, which are basically these colored regions. But the fact you can only define things in terms of clusters will lead to some small changes in the model. But that's all for today.